Welcome to this explainer. Today, we're diving deep into the absolute magic and the fascinating physics of electric drive systems. Have you ever stopped to wonder how a massive construction crane hoists tons of solid steel with millimeter precision? Or how a tiny manufacturing robot knows exactly how much force to apply so it doesn't crush the delicate thing it's holding? Well, there is this incredibly intricate dance of electrical and mechanical engineering happening constantly behind the scenes of modern industry. And today, we're going to unpack the secrets of that dance, starting from the high-level architecture all the way down to the nitty-gritty physics of controlling a DC motor's speed and torque.
Here is our roadmap for today. 1. Anatomy of drive systems. 2. Matching motors to loads. 3. AC versus DC drives. 4. DC motor control objectives. And 5. Controlling speed with resistance. It's a beautifully logical journey, so let's just jump right in.
All right, part 1, anatomy of drive systems, the building blocks of motion.
To really understand how we control a motor, you have to look at the whole ecosystem it lives in, right? A motor doesn't just operate in a vacuum. It relies on 5 core components acting in perfect harmony. It always starts with a raw power supply. But as we'll see, that raw power isn't quite ready for the motor yet, so it feeds into a power converter. Then we have the controllers, basically the brains of the operation managing that converter. This carefully sculpted energy is then fed into the electric motor itself, which acts as the muscle, turning electrical energy into mechanical work to drive the load. Every single piece of this chain has to talk to the others flawlessly.
Now, the crucial thing here is the power converter. It acts as the ultimate translator. You see, you can't just plug a highly specialized industrial motor straight into the grid and expect it to do exactly what you want. The power grid speaks one language, typically a fixed alternating current voltage, but your motor speaks an entirely different one. So, directed by the controller, the power converter reshapes that raw power waveform. Modern systems do this using seriously sophisticated power electronics. We're talking about devices like single-phase, half-wave, and full-wave controlled rectifiers. These pieces of engineering rapidly chop up the incoming AC grid power, smooth it out, and convert it into the highly specific direct current voltage the motor actually needs. And they do this hundreds, sometimes thousands of times a second.
Moving right along to Section 2, matching motors to loads, the real-world physics. We aren't just crunching arbitrary numbers here. We're trying to do real physical work in the real world. That brings us to the unique personality of the mechanical load itself. Just look at this table. Different applications demand completely different torque behaviors. Think about a massive industrial fan pushing air. Its torque requirement is proportional to the square of its speed, which gives it a K value of 2. Why? Because aerodynamic drag increases exponentially. Pushing a little bit of air slowly is super easy, but pushing a massive volume of air really fast requires a nonlinear, massive jump in torque. On the flip side, a hoist lifting an elevator acts way more linearly, and a heavy milling machine requires power that is completely independent of its speed. So understanding the load's unique physical resistance is step 1.
Which brings us to Section 3, AC versus DC drives, choosing the right motor. Now that we know our loads, we have a huge architectural choice to make. Alternating current or direct current. And there is a massive trade-off here. DC motors offer absolutely fantastic starting torque. That is exactly what you need to break the inertia of a heavy load from a dead stop. Plus, their speed control methods are traditionally much simpler. But they have an Achilles heel, the commutator. This is a physical, mechanical switch inside the motor that reverses the current direction as it spins. Because it relies on physical contact, it creates friction and inevitable electrical sparks. That fundamentally limits how fast the DC motor can spin before it basically destroys itself. So, because of these commutators, DC motors need more maintenance, they're heavier, and they're pricier than AC equivalents, which are lighter and cheaper, but historically a lot harder to control.
Okay, Section 4, DC motor control objectives. Hitting the target.
For the rest of this explainer, we're going to focus on those highly controllable DC drives. When we sit down at the controller, we really have 4 main goals. We need to hit our desired speed, provide the exact torque the load demands, do it efficiently, and keep the whole process totally stable. But remember, the motor and the mechanical load each have their own unique torque-to-speed curves. Our actual real-world operating point is the exact spot where those 2 curves intersect. Think of it like a tug of war. If the motor produces more torque than the load requires, it accelerates. If it produces less, it decelerates. This push and pull continues until they perfectly balance out.
And that brings up a pretty pivotal challenge. Since we literally cannot change the mechanical load's characteristics, we can't change the physical reality of a heavy hoist or the drag of a fan,
How do we find that perfect operating point? Well, we have to manipulate the motor itself to force that intersection exactly where we want it. Let's see how we do that in Section 5, Controlling Speed with Resistance, Rheostat Control. Let's look at one of the most classic ways to shift a DC motor's behavior. If you check out this circuit diagram, you'll see that by physically wiring an adjustable resistor, which engineers call it rheostat, in series with the armature circuit, we can choke the electrical current. As we crank up this added resistance, we are effectively starving the armature of voltage. It's a very brute force method, honestly, but by intentionally restricting the flow of energy, we force the entire motor's speed profile to change.
Plotting this out on a graph reveals something super fascinating. The motor's base, no load speed, which is how fast it spins when absolutely nothing is attached to it, stays perfectly anchored. But the moment we apply a load, the slope changes wildly. Mathematically, the speed is determined by the applied voltage minus the voltage drop across our new resistors, all divided by the motor's internal magnetic flux. So as we add more resistance, that voltage drop becomes huge, and the speed just plummets as torque increases. We are physically tilting the motor's operating curve to meet our target load.
Now, if we push this concept to its absolute limit, look at point 4 here, and dial the resistance high enough, the speed drops completely to 0, even while the motor is fully energized and trying to pull. Engineers call this state electrical holding. Under the specific condition, the mathematical speed drop perfectly counters the no-load speed. It's essentially using pure electrical resistance as a frictionless brake to hold a heavy load perfectly steady. How cool is that? But as beautifully simple as this method is, it has a fatal flaw. Adding a giant resistor into your power circuit literally burns off massive amounts of valuable energy as heat. It's like driving your car with the parking brake on. Because of this wild inefficiency, modern engineering has largely abandoned rheostat control for continuous running. Instead, we focus on 3 main methods of speed control, and the other 2 are far superior: voltage control and flex control. Using those smart power electronics we discussed earlier, we can directly manipulate the input voltage for incredibly smooth, efficient speed changes in what we call the constant torque region. And if we need to go even faster, we use flux control, intentionally weakening the motor's magnetic field to push it to high speeds in the constant power region. On top of all that, we use these same sophisticated electronics for smart starting methods, heavily limiting the massive initial surge of current when a motor first kicks on, protecting the delicate internal wiring without relying on those wasteful heat-generating resistors.
So controlling continuous speed with smart power electronics is incredibly efficient, but it leaves us with a really fascinating final question. How does the motor actually know if it's spinning at the right speed? Like if a sudden gust of wind hits our fan or our crane picks up a slightly heavier load, how does the system autocorrect in real time? Well, that requires stepping away from basic circuits and entering the complex world of closed-loop PID control modeling, where precise sensors constantly feed speed and position data back to the controller to make split-second mathematical adjustments. But we will have to leave that exploration for next time. Thanks for joining me on this explainer, and keep questioning how the world moves around you.